So following on from our first video on data formats and understanding binary, we're going to move on to ASCII, which is the way we talk about and store basic English writing and text files, so the Latin alphabet. So ASCII, spelled ASCII, standing for American Standard Code for Information Exchange, came about many years ago in an attempt to make a standard in America for exchanging information on computers. And this standard defined 128 characters, which included letters from the English alphabet, symbols, exclamation marks, commas, things like that. And with it being computers, they also had 32 unprintable characters, and this formed effectively the ASCII standard, if you will, and it was 128 different characters. So that means in terms of a byte, if we opened a calculator and we went to binary and we simply got 8 bits here of a byte, and if we took up the first 7 bits, you'd see that we get 127 in decimal plus 0. So there's 128 different options, and ASCII takes up 7 bits, so it takes up these bits. So the ASCII standard is 7 bits, and it's the lower 128 values of a full 8 bytes. And that means it's up to from 0 to 7F in hexadecimal. And the problem was, well, I say a problem, at first there was no problem. So in a file you could store A, B, C, D, E, F, G, you could store A, B, C, D, E, F, G in capitals. And if we save this file and open up, say, hex dump in Visual Studio, and we open this test file, and then we take a look at the hex, you can see A, B, C, D, E, F, G, A, B, C, D, F, G, and here's the hexadecimal values. So 41 in hex is 65 in decimal. So the uppercase A is 65 in decimal, and then 66, 67. And this forms the whole ASCII table. It's simply stored in a value from 0 to 7F in hex, so you'll never see anything above 7X for the true ASCII values. So you can represent every single ASCII value by going between 0 and 7F. So I made a quick application here, which you'll come to this bit in a minute, but for now I just make a range. So if we change this to 0 to 128, then we basically create an enumerable range. This just simply loops, if you will, from 0 to 127, because that's the length, the number of times. So this goes from 0 to 127, and then we cast it to a character for that value. So we'll cast it to a character for the value 0, then 1, then 2, then 3, and so on. Turn it to a list, enumerate the list, and print out each character on a new line. So if we run this now, we should see that we get every character printed out. So we start from 0, which to 32 is unprintable. So these are the special characters like new lines, tabs, making sound, all values that don't represent a printed character. And then if you get to 32, it starts with the exclamation, then the quotes, and the hash, the dollars, and it carries on down. And this I've printed out also the actual value here, so the 0, 1, so we can see. So as you see here, 65 in decimal is the capital letter A, and then there's all the alphabet printed out and a couple of symbols, and you finally get down to the bottom there. So this is effectively the ASCII table. This is what we mean when we talk about ASCII and pure ASCII. This is the whole thing right here. So you can run this code and see it, and you can also see it on a website that I've got open. So we're going to go through these in order. I've found some good reading points to supplement the video. So if you go to C++, like typed out.com/doc/ASCII, you can see here they've done a write-up on ASCII in a bit more detail. And they've also dumped in here the table we've just been talking about. So there's 0, 1, 2, 3 across. Let's go to the next line, go across. And to turn it into your values, you can just cross-reference the table. So you can see you've got all the values we've just printed. You can also just Google for ASCII table, and there'll be hundreds of different visual tables to show you these values. But the reason I picked this website is because it goes on a little bit to show these what's called extended tables. So ASCII in itself, and pure ASCII, is just these first 128 characters, and that's all it ever represents, and it represents the same thing on every computer and everywhere. So that is a hard defined thing. So the first 7 bits in the ASCII table, which is effectively the whole ASCII table, is always these characters. And they're represented by simply creating a byte on a computer, as we have done. So we just created a character which is, it can represent obviously more than that, but we could turn it into a byte if we wanted. It still does the same thing, just won't display correctly there. So a character will naturally take in a byte and display it as if it was a single byte. That's no problem. So we've done it to output a value. So if we ever wanted to write a specific value, or do it wherever we wanted, we could do console.writeLine and then just do 65 for writing out a byte. And the first one now should be the capital letter A. Again, have we cast it to a character so it prints correctly? Or EO, something's gone wrong there. Okay, let's just change it to, if we're doing hex, it's 4-1, not 6-5, that's why. There we go. So you've got the capital letter A. So ASCII you can simply create via making the bytes themselves, or you can type in an integer of 65 and cast it to the same thing. You can represent it however you like, but the bottom line is the underlying value is simply the first 7 bits of a byte. So hopefully that, along with a quick read up on this website and any others you need, should give you an idea of what ASCII is. But like I say, the simplistic solid answer is ASCII is the first 7 bits of a byte that always represent this specific set of data. And that's how we originally communicated over computers and over any form of digital communication. We represented these values here. Now the issue come when we were then going multilingual. We were extending outside of the US, and we wanted to talk to other countries and other languages, and we soon realized that obviously 127 values is nowhere near enough to represent most languages. So we've got, Chinese has got a huge amount, Arabic's got thousands, so you cannot possibly represent it with 127 bits of information. So we'll step back a little bit before delving into how we solve that issue, and what happened as soon as the ASCII standard come out and 127 bits of information were used in a computer's byte. So if we look here, we've got this 1 byte left, and computers have always stored in 8 bits, if you will. They've always worked in bytes in general. So everybody that started using the standard was like, well, I've got this extra bit, which means I've got another 127 values. So everybody had this idea at the same time, and everybody started creating their own versions of what these extra values should represent, and what these symbols should represent. So on computers, if you then put in a value of 255, what's that meant to be? It's not defined anywhere. So people started making these extra values, and these were typically, the official definition for them is a code page. But in the original DOS machine, so MS-DOS and all the older computers around that same era, created this OEM standard. I think IBM created the standard, And if you've ever seen in like Windows 3.1 and maybe on some computers in stores, you'll have noticed they've drawn like boxes around things and put advertisements in, or in a DOS command prompt to highlight stuff, they've drawn things. So these characters might look familiar to some of you, and these are the characters that were used in the extra 128 bits of a byte. And it was simply interpreted by the machines at the time that this is what they will represent. There was no hard defined standard. It was up to the manufacturers and the creators of systems to decide whether they did this. But most places and most companies started using this, what's now called the OEM extended ASCII. So this first bit here, as you can see, is 80, which in decimal is 128. So this is the first bit of the new extended piece of information. So if we then went to this first bit enabled, you can see we've got 80. It would originally represent this on a DOS machine. So you'd have the C with an underline. And then as you go up, now all these values you can represent. Once you toggle this 8th bit, then all of these are going to define this table. And that's how it happened back then. But as I mentioned, the problem was everybody at the same time had an idea of what this extra piece of information should represent. So they all started making their own different tables. So this is one table, and this was the standard for like MS-DOS and what most of you are probably familiar with. But then what happened was, if we go to Wikipedia and type in code page, you'll see that basically, again, this will give you more of a read up on the history that I'm not going to bother going through, but you can see here it starts with MS-DOS and IBM created the initial one and blah blah blah. And then what happened was, each one of these is a way of representing the extra 128 bits in the code pages, and then these will go on to define things outside of those. But in general, you'll find here is the bulk of the standards of what become the code pages. And I believe 1252, so this will be ANSI 1252, is the definition of the Latin alphabet in the extra 128 bits of information. So you can see here again, you've got the whole set going right the way down to the 128, which is up to there. So all that is standard ASCII. And then it's this bit you're interested in from here to here is the new, this is the code page right here. So this is the code page we're talking about. And the standard for this is called Windows 1252. So we've got that open here. I'd already pre-opened it for you. But this is what we're then looking at on modern computers. So if now we created a file in using this code here, which you can simply look at and copy yourself, it just does the same thing here, creates a range, but creates the whole range of a byte. So it includes the extra 128 bits, and it writes it to a file. So here's the file. So this Visual Studio Code doesn't represent it correctly, but we can see in the hex dump, so ignore this bit here, that isn't shown right there, but you can see here the file is nothing more than a bunch of bytes from 0 to 255, so it literally goes 0, 1, 2, 3, 4, 5, all the way up to 255, and that's all the file is. So if we open that file in Notepad, which we have here, you can see this is the output. So the first bit will be the 0, up to here will be number 65 in decimal, and it goes all the way up to here, which is the first 128 bits of information. So this is the ASCII data, and then this is the extra 128 bits of information. So this is the code page. This thing afterwards, values that are represented after 128. So starting here, this is where I've then dumped out the values from 128 to 256. This has given us this information. And if we then look at this, you'll notice that they match. So if we have this open, you'll see that the first one is this symbol, and then that's missing because it's not a printable character, and then it's like a comma but with a visual style to it, and then the F and so on, and it ends with the Y. So this can change on every machine, and if you've seen in the file format, there is no kind of definition to this file format. It doesn't define what it is or how it is. It's simply a dump of bytes. There's no header, no tag for the machine that's reading this file to know anything about it. So it simply has to make a presumption that this is an ASCII file if it wants to open it as text, say. And then it also has to presume what code page these bits or these bytes are relating to. And as we've seen, there are many different code pages. So if we went to Greek, then the machine might expect to interpret them differently. And you can see 255 is different, and all these are now the Greek alphabet. So you could open this up on a computer that has somebody's language set to Greek as the locale, and they could open this exact same file and it would show differently. It would show these symbols instead of these symbols. So there was a major issue with ASCII and what they called the ANSI standard. So it still exists in Notepad if we did file save as, and you can see it here, encoding ANSI. And this is a real typo that still exists in Windows 10. There is no such thing as just an ANSI encoding or format. It needs to be a specific version. So it needs to be like ANSI, ANSI 1252, for example, or 1253. It needs a number. But because Microsoft back in the day didn't really know much about encoding or multilingual, believe it or not, they simply interpreted the ANSI as a format in itself, an encoding in itself, and disregarded the prefix or the postfix of 1252. So that's why it ended up in Windows and ended up being simply defined as ANSI, and it's technically wrong, but if we save, then it's usually, certainly on my machine, it will save as this Western format. But again, the underlying issue is dependent on the receiver of the file or receiver of the data. They could well be using any one of all of these different code pages, which means the values you're trying to represent to them won't necessarily match. They could be different values, and they are, and that's what happened. So all of these different representations of those 128 bits were called code pages. You can find them all here to read up more. But basically the standard on Windows machines was defined as this 1252. So that's where we got to with that. So the mess that was evolving around the ANSI and the format there, and extending out of 128 bits and then going beyond also to correctly represent all of Arabic, formed Unicode. So we'll do Unicode in a separate video, but if you can imagine, if we looked at the Arabic here, this doesn't represent all the values. It represents hardly any of them. So there was also a need, in many other languages to accurately represent all of these values, and also to have them so that every country and every machine and every standard, regardless of language, represented the values the same instead of differently. So instead of having, we go to here, instead of just having a single byte and nothing starting the file and no understanding of this structure, we needed a proper file format. Something that defines, when you open this file, what is the file, how is it defined, what does each byte mean, what happens when I want to represent 64,732 in a single file at a certain point. Well, the files are made up of bytes, so you could combine bytes together. But if you then decided, if you represent, let's try and make it easy to understand, if we have a hex value and we want to represent, say, FF, that's fine, that fits in a single byte. But say we want to represent FFE3 or 65,507, and that's in the middle of our file. Now, if we were also representing just the letter 1, or rather the number 1, you want to use a single byte. So you'd have, say, I want to represent 0, then I want to represent 1, then in the middle I want to represent this much larger number. So then would you just put FFEEE here? Then how would you know that these 2 bytes should be combined, as opposed to it being to actually represent FF on its own, if you're trying to represent 255, or are you trying to combine them? So this issue, it's fairly easy to solve, and I say easy, it was a lot of work, but it might seem easy now. But this was solved with Unicode, which we'll come on to in the next video. But hopefully this is explained the basics of ASCII and what ASCII means when you hear the word ASCII, and it's also overused and misunderstood, and people think it represents all of the values. But all you have to remember is ASCII is simply the first 128 bits of information from 0 to 127, and it represents the Latin alphabet, and it's always the same symbols. And those symbols can be found by just Googling or going to pages like this, and it's always this set of data, this set of represented characters, and it never changes. That is ASCII right there. And then when the confusion starts is when you start talking about extended ASCII or code pages beyond this point, and that's really when you want to move to Unicode. So if you ever start delving past 127, you really want to not save your file as just raw bytes. You need to start adding Unicode formatting to the file structure, or some kind of structure, so that this specific code page, if you will, or the whole code pages of information are defined and explicit, so they can't be misinterpreted. So all that will, code pages and that kind of interpretation will come more in the next video with Unicode. And then anybody wanting more information and a longer read up, I've tried to Google for a good resource to find something good for you to read and sit and get a bit more technical info. And this seemed to be a really good article, so I'll post this link in the video, or you can just Google for this title or this guy here and I'm sure it'll pop up. But this gives a really detailed background of basically what we've just talked about, but with a bit more technical detail and a few more links. And again, it goes over the problems, and then it also starts delving into Unicode, which I'll cover next. And I'll go into detail of exactly how Unicode works. But you can sit and read this whole article if you like, and get some information that you might feel is missing. Or again, just comment in the video, and I'll answer any way I can. So sometimes I explain it one way, and other people might need explaining differently. So if you don't understand something I say, I always answer the comments, so simply leave a comment and I'll try to explain any misunderstandings or confusion you might have. But hopefully that was enough for you to understand and clear up the mess around what ASCII really is, compared to when people are talking about things and the extended code bases and code pages and things like that. So hopefully that was useful.